So basically identifying the three general factors that influence the way at which a substance can be passively transported across the membrane, and the two general factors that influence the rate of active transport. So when we speak of the rate of transport or the rate of movement of particles across a membrane, we also need to understand what the diffusional equilibrium is. The diffusional equilibrium. And this is basically a state where there is no net transfer of molecules across a membrane. Now bear in mind we're implying or we're understanding that this membrane is permeable to the molecules in question. But at diffusional equilibrium, although there is still movement, there is no net transfer. What do I mean by net transfer? I mean that one side or the other does not accumulate more particles than on the other side. Okay, so there's still movement happening across this membrane, but neither side will accumulate an excess of molecules on either side. So for example, in A of this image, there's a concentration of 1 moles on side 1, whereas there's also a concentration of 1 mole on side 2. And although there is free movement happening across this membrane, there's a one-way flux happening across this membrane, we do not have an accumulation of an excess on either side. Okay, that is what we call the diffusional equilibrium. In the scenario B, there is not diffusional equilibrium, simply because on side 1, we do accumulate more particles. We have 2 moles on side 1, whereas we have 1 mole on side 2. Okay, and so this scenario, this cell is not at diffusional equilibrium, whereas this first scenario is. Okay. So let's talk about passive transport, and let's talk about it in a little bit more detail. We did introduce it last time we met, but some of the characteristics are that it is spontaneous, which we said. It's that downhill movement, and it requires no energy. No energy input is required to move molecules or to move solutes or particles passively, right? Passive transport does not require energy. There are 3 types of passive transport that we're going to speak about. The first one is simple diffusion. Simple diffusion, nice and easy and simple. There are no transporters required, no channels required. Okay? Particles are going to be moving according to their concentration gradient, and this requires no energy. And then there's facilitated diffusion, which, as the name implies, requires some sort of mechanism, as well as diffusion through channels. Okay? So let's start off by looking at simple diffusion. Now, as we just mentioned, there are no membrane proteins required. Okay, and transport happens freely or simply through the phospholipid bilayer. Now, what does that imply about the particles or the molecules being transported? What does that imply about these particles?
Non-polar.
They are most likely non-polar. Want to add something, Madeline? No? Anything else? They're small. Perfect. So they're most likely small, non-polar, non-charged particles that will freely move through the phospholipid bilayer. Okay. Factors affecting the rate of simple diffusion are going to be the magnitude of the driving force. Now, as we'll see a little bit later, the driving force here can either be the chemical or the electrical driving force, but it is most usually, or it's most likely, the chemical driving force. I'll say that again. The driving force that we're speaking about here is most commonly the chemical driving force, but we can take the electrical driving force into consideration. Okay. The second factor that affects the rate is going to be the membrane surface area. This is going to be very important here and in some other systems coming up. The membrane surface area is going to directly affect the rate of movement. And finally, the membrane permeability. How easily do particles go through that membrane? Okay.
It was commonly, the driving force was commonly which one?
The chemical driving force. Chemical driving force. So the magnitude or the strength of that driving force, usually the chemical driving force is what we're referring to here. Okay, so let's take a scenario. Let's see how we're doing with time. Okay, so let's do this. Yeah. Okay, so let's look at simple diffusion here. Okay. And what we're really talking about here are factors that influence the strength of the rate of simple diffusion. Okay. What are the factors that influence the strength of the rate of simple diffusion? So let's look at 3 cells. Cell 1, cell 2, cell 3. And let's say that there is a membrane dividing both these parts of the cell, okay, such that there are some particles on either side. Okay, so in scenario A, we have, let's say, 1 mole of particles, 1 mole of particles, and on the other side we have 0. So this will be plain water. This has no solutes. In scenario B, we have about 0.8 moles on the left, and then let's say 0.5 moles on the right. Okay, so we have a little bit less than on the left. And then in scenario C, we have about 0.5 moles on the left, and then an equal amount, 0.5 moles on the right as well. And this is confusing. Okay. Now, in that first scenario, what we'll see is that there is a strong rate of simple diffusion taking place across this membrane. Why is that? Why is there such a strong rate of diffusion taking place across this first membrane? Good, we have a concentration gradient. We have a concentration gradient established here. So the chemical driving force here is going to attempt to equalize the particles on both sides. Okay, we have a strong concentration gradient. Now in the second scenario, we have less of a difference, right? Less of a gradient, don't we? Okay, we have some particles on this side and then a few more on this side. So we have a smaller gradient across this membrane. And so we will have some movement, but it will be less. It will be a smaller amount or a smaller magnitude than in scenario A. Okay. And then finally in scenario C, do we have movement here? Do we have movement here? We still have movement, right? But do we have net movement? We have no net movement, right? No net movement here. And why is that? Because they're equal. They're equal. And so we don't have a gradient where particles want to go on either side. They will continue to move freely, right? Remember that diffusional equilibrium that we spoke about, but there will be no accumulation of excess on either side. There will be no accumulation of particles in excess on either side. And although we have free movement, so I'll put here, Particles still moving. Okay, so although the particles are still moving, we have no net accumulation on either side. Okay, so these are some of the factors that affect the rate of diffusion, or the strength of, or the magnitude of the diffusion. Okay, any questions on that? All right. Okay, now we'll probably just wrap up talking about this, and then we'll call it. Oh. Okay, so let's just wrap up with these two slides, and then we'll call it a day for today. So basically, what we just saw was that the magnitude of the driving force, how strong that concentration gradient was, is going to determine the rate of simple diffusion. If we have a higher gradient, which we saw in that first scenario, we're going to have a stronger movement, a faster rate of diffusion. And so if we plotted these two things on a graph, the concentration gradient versus the net flux, and flux just means the movement of those particles, okay, the net movement. We would see that as the concentration gradient increased, the net movement, the rate of movement, okay, across that membrane would also increase, okay? The second factor that affects the rate of simple diffusion is the membrane surface area. How much surface area are we working with? In these two images, we're looking at the alveoli of the lungs, and on the left, you can see that there's lots of surface area here. And the more surface area we have, what does that tell us?
More permeable.
It's not more permeable, but we'll have more movement, right? Just in the way of having more area. So this is seen in the lungs, it's also seen in the gastrointestinal system. Having greater surface area improves the rate of diffusion simply because we have more membrane space to move across.